Okay, let's move on with the network layer, which is conveniently provided to us in the internet with the Internet Protocol. Internet Protocol is the common language, the lingua franca, of all the hosts connected to the internet. Currently, we are mostly using IPv4, but we are in the process of slowly transitioning to the next version of IP, which is IPv6. Now, the functions of the internet or the network layer and the internet protocol are one of the very few examples of the things that we usually want you to know. Okay, so it is very often we ask this question: what is the functionality, the core functionality provided by the internet protocol? And we want you to answer unreliable communications, connectionless communications, best effort diagrams, datagram service, to the transport layer. So what these words actually means? Unreliability means, in this sense, that even though the IP protocol is supposed to be able to connect any two hosts connected to the internet, this promise is not reliable. So whenever you send the packet from one host to the other, there is no guarantee that that packet will safely arrive to the destination. So this is again very much akin to the way the postal service actually works. Whenever you just drop your envelope into the post box, you can never be sure that the postal service will be able to process or just send your transmit your mail to the actual destined or party. In fact, in very often they actually just lose your mail. This is the same thing with the internet. Whenever you just send your packets into the internet, there is no guarantee that it will find the destination, or that the actual payload that you send will not suffer any errors. So it can very well happen that something will arrive to the destination, but will be completely unable to decode that. Okay, the IP service is completely unreliable. We have header checksums, so the IP protocol layer makes sure that no errors occur on the IP header, because that would be devastating, like sending one packet instead of its intended destination to another destination. The internet makes sure that this never happens, because whenever the header checksum shows that there is an error in the bit error in the IP header, the datagram will be dropped. But in other respects, there is no checksumming on the payload. This is the functionality of upper layer protocols. So the first principle here that you need to understand is the IP is connectionless or unreliable. Connectionless on top of this means that there is no connection set up and tear down before and after the communication. Recall that it makes sure that the network will not need to store per session or per application exchange information, which makes it possible that the IP infrastructure can scale to these sizes that we know today. The third principle is the datagram service, which essentially means that this is the analog of the postal service. Every datagram corresponds to an actual postal service mail, in the sense that every packet's IP header contains the full destination address and the full source IP address. And this makes it possible to route all your packets individually through the internet, because all metadata that is needed to get your packet from the source to the destination through the internet is there in the IP header. This is again very similar to mail envelopes that have all the addresses of the sender and the receiver. And the fourth principle is the best effort service. So in principle, all packets are created equal, which essentially means that there is no differentiation between the different packets of the different parties. Your packet, my packet, whitehouse.gov's packets, they all treated the same in the internet, regardless of the sender or the receiver. We have a question mark here because this principle is questioned every day these days. If you've heard about the network neutrality debates, these are basically all about this best effort principle. Here are the services that the IP layer provides to the upper layers. First is internetworking. So IP provides worldwide connectivity. Recall layer 2 provided the connectivity between any two IP hosts connected to the same IP net or the same Ethernet network. Internet network, the Internet protocol makes it possible for any two hosts to send packets to each other, regardless of whether or not they are in the same Ethernet network or not. Or same Ethernet local area network or not. So the IP provides global routing of traffic between heterogeneous devices, subnets, operating systems, link layer protocols, etc., etc., etc. Addressing, so there is a global, so there's a way to identify IP hosts globally, not just in terms of location, so where a particular IP host is, whether your laptop or your mobile is correctly connected to the BME's network or your home network. The internet makes it possible for your device to actually receive packets. This basically means that host ports are endued with unique IP addresses. The third service is routing and forwarding, and recall that these two things are different. Forwarding is done one by one, packet by packet at routers, by looking up the destination address in the forwarding table stored at the IP routers to find the next hop addresses. Routing is the process of maintaining the forwarding tables, and of course there are also other services that we will not discuss here, fragmentation, etc., etc. IPv4 and IPv6 differ. Conventionally, IP as of version 4 uses 32 bits IP addresses, which allows us to connect roughly 4 billion hosts to the internet. We for a long time ran out of assignable free IP addresses. So we are transitioning to IPv6, which introduced 128 bit address space, which is theoretically enough to address any particle in the universe. Transition to IPv6 slow, but it's ongoing, and the use of IPv4 is still pervasive, and we do not expect it to go away soon. So here we only just discuss IPv4, but of course IPv6 is equally important, and please make sure that you are aware of the basics of IPv6 as well. The IPv4 header is here. I will not go into the details. Please make sure that you know what type of service or the internet header length field is, and what is explicit congestion notification, how IP fragmentation occurs, what's the functionality of the TTL. The only important part here is the protocol identification, which identifies the upper layer protocol of this encapsulation, and the source and the destination addresses, which are recalled in IPv4 are 32 bits. Here's addressing is a bit complex in IPv4, and since it turns out that many of you believe that you know how to handle IPv4 addresses, in practice it quite often turns out that you don't. So let's just make a very quick run through how addressing occurs in IPv4, and let's just make sure that you are well aware of what an IP subnet is. So theoretically, IPv4 addresses are 32-bit unsigned integers, which makes it possible to address roughly 4 billion different addresses. The problem is that if you write these addresses down in decimal, this is fairly difficult for humans to handle. Okay, so for instance, it's very difficult to remember. Now maybe the addresses are much simpler to handle in binary form, okay, but this is perhaps even more difficult to remember. So this is the exact same address that we see here in decimal, but it's just in binary notation. Computers can handle the binary notations. In fact, they do. But for us, we need a different notation for us to be able to understand, and this is what's conventionally called a dotted decimal notation. We take this 32-bit IP address, break it up into 1-byte decimal numbers. There will be, of course, 4 1-byte decimal numbers, and then we read all these numbers one by one to get this dotted decimal notation 152.66.244.111. Okay, this is again the same IP address, but now we essentially obtained a form that might be easier for humans to handle. Please make sure that you know how to transition between these two or these three formats. Originally, we used to have classful IP addresses. In a moment, you will know what it actually means. Since 1993, we transitioned to classless interdomain routing. Again, we'll in a minute learn what this actually means. Certain sets of consecutive IP addresses are called subnets. We've already seen one subnet. These were called the physical subnets. So for hosts connected to the same link, conventionally we assign a separate IP subnet to number all the different hosts within that subnet or that local area network. This is a physical subnet because there is an actual LAN, a local area network, that corresponds to the subnet. But there are also logical subnets, so we can actually create logical subnets which for the rest of the internet look as if they were physical subnets, but we as operators know that this is not the case. Okay, so for instance, BMEnet belongs to a single subnet. This is a 152.66.0.0/16 subnet. Okay, so this is, as you can see, a fairly large subnet. It's called the class B subnet. What turns out that this is an actual subnet for the rest of the internet, regardless of the fact that there is no local area network that would connect all the hosts connected to the IP to the BMEnet to the single physical net. This is because the operators on the of BMEnet actually created a logical subnet. And this exists just for routing purposes. So the idea is that the subnets appear to the rest of the internet as a single IP address prefix instead of separate per host IP addresses. So for the rest of the internet, it is possible to handle all the IP hosts connected to BMEnet with a single IP prefix in their forwarding addresses. So for instance, whenever you send a packet to any host that are currently connected to the BMEnet, say from the United States, those routers in the United States do not need to know the whereabouts of every single IP host within BMEnet. They only just need to know that this host address that we are trying to send the packet to belongs to BMEnet, and that BMEnet has a particular next hop to send the packet to, but you don't have to be aware of the location of every IP host in the in those subnets. Okay, this makes it possible to aggregate state, one prefix for potentially thousands of millions of IP hosts. We are going to see this aggregation in operation in the rest of the lectures. It's just basically the only thing you need to know, that we have logical and physical subnets, and these two things differ. IP addresses have two parts. The first X bits are called the subnet identifier. This is the set of bits that identify a particular a subnet. For instance, for anything connected to BMEnet, the subnet identifier is 152.66. This is a 16-bit long subnet identifier. The rest of the bits are called the host identifier. So within the subnet, the rest of the decimals or the rest of the bits identify a particular host within this subnet. And here X is called the prefix length. Okay, so for BMEnet, the prefix length is this 16, which essentially just identifies the bits that belong to the subnet identifier, and of course also the bits that belong to the host identifier. The nice thing in the current internet routing and in classless interdomain routing that X is not fixed. It can be of any length between 0 and 32, and this makes it possible to play very funny tricks in IP routing. This /16 or /18 here can also be written in the traditional netmask form, but I strongly advise against this because this is somewhat more difficult to process for humans. Originally, we used to have classful addressing in the network or in the internet, which basically means that for any subsets of the internet hosts, the prefix length was fixed. So whenever a packet, whenever an IP address used to, at least before we transitioned to classless interdomain routing, the rule was that whenever an IP address starts with a 0 bit, then it was supposed to belong to a /8 IP address range. Okay, now this makes it possible to basically, this is a huge subnet because only the first 8 bits are the subnet identifiers, and for host identifiers you can use 24 bits, which corresponds to roughly 16 million IP hosts. So these are huge address spaces. Whenever the IP address starts with 10, conventionally this is supposed to belong to a /16, and as you can see, BMEnet's IP addresses and IP address range belongs to this class B of IP addresses. Class C starts with 110, and here the host identifier is supposed to be just 8 bits, while the subnet identifier is 24 bits, which makes it possible to address only 256 nodes. Class D and Class E are for historical reasons. Now the problem here is that this was not really flexible. It was not flexible enough for the internet. From 93 we transitioned to classless interdomain routing. Any address range goes with any address prefix, but at this point we have to specify the subnet mask and the prefix length. Okay, so here is, for instance, an IP address range in the so-called classless interdomain routing notation. So the dotted decimal notation with the prefix length, we see that the subnet identifier here is 18 bits. This is the first 18 bits of this, the first 18 most significant bits of the IP address range. You can of course convert this to a subnet mask. Just take this, just set all the subnet identifiers with the first 18 bits of the address range, and set the rest of the bits to 0, and then just convert this into a dotted decimal notation. And this is so the first subnet identifier bits are 1, rest are 0, and just convert this into a dotted decimal notation. That's going to be the subnet mask. Okay, the question is which is the first and which is the last IP address that can be assigned from this range. We know that the rest of the bits here, these are the host identifiers. Okay, and the first IP address can be obtained from this binary notation by setting the last bit to 1. Okay, so this guy, this is the first IP address that we can assign from this address range. This is 192, that's the 168.192.1. The interesting part here is the last IP address. What you can do here is that set all the bits, the host identifier bits, to 1 except the last bit, which is 0. Okay, and then just convert this into a dotted decimal notation. As you can see, this third decimal is changing now. Okay, why we don't assign also the host IP address where we have 0 bit in the last position. This is because that's actually the subnet identifier itself, and in many cases this would produce controversy. Similarly, we usually don't assign the last bit or the last address from IP address range, because traditionally this is allocated for multicast, the subnet multicast address, even though we don't use this anymore. For security reasons, conventionally we don't allocate the very first and the very last IP address from an IP address range. Now, using this little tool, now we can, or this little introduction, we can now decide a simple questions. For instance, does this address .199.100 belong to the previous address range? How do you actually just do that? Again, take the IP range in CIDR notation, take the subnet ID, remember this is the first 18 bits, then take the IP address, similarly take the first 18 bits and compare. If these two guys are actually the same, that this means that the subnet identifier of our IP address is the same as the subnet identifier of the IP range, which per definition means that the subnet IDs match, and yes, the address belongs to the subnet. Please try to practice, because this can be really tricky. Sometimes this can really trick you. A little bit of terminology. The routing table, which we usually call the routing table, is called the routing information base, and the forwarding table, or the FIB, is a different concept here. What's the difference here will be made clear very repeatedly in the rest of this lecture. It's just at this point it's very important to know that routing does not equal forwarding. So forwarding here is this functionality of a router which makes it possible to pass one packet on from one port to the other, and the routing is the computation of the forwarding passes and the forwarding table to find those next hops. Okay, the steps of IP forwarding. The IP router is a device dedicated to IP level packet processing. In these days we tend to use the word switch much more than a router, so very often a switch also does IP routing, but traditionally IP router used to be a layer 3 device, so an IP protocol layer device. The idea here is that an IP router can have, say, 48 different ports, and all these different ports can have IP addresses from different Ethernet LANs, and then the idea in the IP router is that it will be able to pass packets on between these different Ethernet LANs. And how it's actually done? By looking up the destination address in the forwarding information base, and how we actually maintain this forwarding information base is by using the routing functionality. There are lots of miscellaneous services in an IP router which are not important at this point. The idea in IP routing is that IP routers usually run routing protocols. There can be multiple routing protocols per router, for instance OSPF plus BGP. They exchange topology descriptors between neighboring routers, and then using these topology information or this pass level information in BGP, each routing protocol can set up its own view of the network and then create a RIB, which is essentially a routing information base which contains IP prefix to next hop associations based on the information learned by the particular IP routing protocol. And then using these RIBs, the router distills the forwarding information base by selecting the best next hop for each subnet prefix stored in any of the RIBs, and then downloads this FIB into the data plane, and then the router will just use this FIB to actually forward packets. Here is the steps of IP forwarding. First, the router, when it receives a packet, checks the packet's validity, so the IP headers, versions, and options, etc., performs IP lookup, so based on the destination address of the IPv4 header, by performing its longest prefix matching from the forwarding information base to find the smallest known subnet that still contains the address. What this actually means will be made clear in the next slide. The idea here is that from this point we know which is the neighboring IP router or the neighboring IP host to which we have to forward this packet to. So for the rest of the steps are just related to actually getting this packet to the next hop. First we need to handle the packet, which usually just means decrementing the time to leave field, and if the time to leave falls to 0, we just drop the packet, set the checksum, etc., and then forward the packet to the next hop that we found in the fib. So the idea here is that we do hop by hop routing, which means that the routers do not know that the entire explicit path from themselves to the destination. They just only know the next hop along the forwarding path. So they just only know, okay, I don't know where this destination actually is, how to actually get packets on, but I know a neighbor that will know, or that will have a better information than me, and I just pass the packet on to this neighbor, so that it can be able to packet to send the packet hop by hop towards the destination address. What longest prefix matching is, if multiple subnets match an IP address in the forwarding information base, that we need to find the most specific match. So this is the subnet whose subnet ID matches the packet's IP destination on the most bits, counted from the most significant bit. So I let maybe a moment for this to sink in, because this is one of the most complex and most difficult to understand concepts in IP forwarding. This is not your everyday virtual circuit switching use case or Ethernet MAC lookup case. This is much more complex. Longest prefix matching is much more complex than all other routing protocols forwarding functionality. The idea here is that we need to find the smallest subnet that still contains the destination address from our forwarding information base. We are going to see an example in the next slide. This is called longest prefix matching, and this is key to IP. Okay, so we are going to just return to this thing a couple of times in the rest of the lectures, because this can be used to implement lots of useful tricks. Problem here is that this makes IP forwarding quite complex, as fib lookup is non-trivial due to longest prefix matching. Here's an example. We have a sample forwarding information base. We have IP prefix to next hop mappings. So the idea here is that whenever we have this entry in our forwarding information base, this essentially means that if we receive a packet and the packet's destination address belongs to this subnet, okay, then we need to pass this packet on to this particular next hop IP address. We don't know whether that next hop belongs to a router or an IP host, whether that is the destination or just the subsequent router along the path of the packet. We only just need to know that that wherever this IP prefix matches the destination address, then this is the next hop that will need to receive this packet. Okay, the problem here is that any particular IP address might be matched by more than one of these little prefix to next hop map rules in the forwarding information base, and we need to decide which one to apply. Okay, so wherever we have, for instance, an IP address 192.168.1.1, this matches, as we're going to see in a minute, these two guys. Okay, the first and the second entry in this forwarding information base. Why? The first 16 bits, okay, these are all belong to these two decimal numbers. They are of course the same. Okay. The only interesting part here is the rest of the bits. Okay. In the actual IP address, the 17th bit is 0. So this trivially matches the first destination address, or the first entry in our fib. And of course, since this is 0, this also matches the second one. Okay, so we have these two matches. The first matches would instruct us to send the packet to 10.0.0.1, while the second entry instructs us to send the packet to 10.0.0.2. Now, whenever such a situation arises, so multiple entries match a particular destination address, then we need to find the one which has the longest prefix length. So in this case, the second entry wins, okay, and we send the packet to 10.0.0.2. Okay, why? Because the rest of the bits do not match. Okay, so we have this guy will not match these guys, and of course this guy either. So the third and the fourth positions. So we have a difference there, and so entry 2 will be preferred. There are further examples here. We're going to have a lab to practice this, but please make sure that you understand this, because in the midterm you will definitely get an exercise that will try to ask you to perform longest prefix matching by hand. And this will need to have, so you will need to have a good understanding of what's going on here, because longest prefix matching is key to IP forwarding. A final note over IP. IP over Ethernet is a little bit special because there is a little additional functionality, the address resolution protocol, that we need for IP to work over Ethernet. The problem here is that whenever we send an IP packet, okay, of course we know the payload and we know the IP headers, source and destinations, but in order to be able to send this packet through these subsequent switches, we need to know the destination Ethernet address or destination MAC address. Okay, of course we know our own source MAC address, so this guy is well known, but in order to be able to fill the Ethernet header, we need one information that usually we cannot be aware of. This information is which is the destination MAC corresponding to 10.0.0.2. Okay, we cannot really know because this is Ethernet level information, so the IP layer does not know it, and the Ethernet layer does not know this either, because the 10.0.0.2 is an IP layer information. So we need some intermediary, and this is the address resolution protocol, which makes it possible for C1 to ask on this subnet which is the destination MAC address that belongs to my IP address 10.0.0.2. And then whenever an ARP query is sent into this subnet, this will be received by all the hosts connected to this subnet, because it will be sent to the Ethernet multicast or broadcast address. And then what happens here is that C2 will recognize that someone is actually asking the MAC address corresponding to its own IP address, and then we respond with its destination MAC. And this destination MAC will be written here, and then we can finally send the Ethernet header through the Ethernet link. Please make sure that you understand the ARP. There will be, I think, a lab exercise corresponding to this. We don't have time to look into the transport layers. So these are all the things that work on top of IP, which makes it possible to communicate for any two users or any two applications on any of the hosts to communicate with each other. The basic concept that you need to know here is the notion of a UDP or a TCP port, which identifies an application or so-called socket on a particular host. So the IP address identifies the hosts, and the port identifies the particular application, be that a web server or a DNS server or whatever, that runs on the host identified by the IP layer. There are two protocols here, TCP and UDP. TCP is connection-oriented, reliable transport between two unique TCP ports, and UDP is the complete opposite. So it's connectionless, non-reliable datagram service between UDP ports. We don't have time to look into TCP, but please make sure that you understand everything here. So what's connection-oriented, what is reliable, and what's an actual stream? What's a byte stream? This is very important. You need to know how TCP flow control works, how congestion control works, okay, and why we can multiplex multiple application layer sessions as to a single TCP connection. HTTP2, for instance, uses this idea extensively. The complete opposite is UDP. So this is connectionless datagram service. This is actually just a very shim layer on top of IP, which essentially just contains only the source port and the destination port to be able to identify the applications, but nothing really more. So it's essentially just a fancy form of IP and provides us unreliable and a connectionless datagram service. There is no connection set up here. So that's all for the TCP IP tutorial. We have just tried to revise all these functionality that just is needed for any two hosts, any two applications to exchange data over the internet. The rest of the lectures will be mostly about IP, but we need you to be aware of that there is a fairly complex machinery below IP and on top of IP. And this all belongs to the Internet Protocol suite. Of course, our attention is IP because IP is the largest common divisor in the Internet. Every packet sent from any application to any other application on the Internet will go through the IP layer. It will be processed through that. Okay. On top of IP, there are lots of protocols. Below IP, there are lots of protocols, but IP is the lingua franca. This is the single point that processes basically all protocols. Okay, every host speaks this. This, on the one hand, makes it possible to every two hosts that implement IP to exchange packet, but this is, on the other hand, is one of the most problematic issues with IP, is that it's basically impossible to innovate or change IP at this point, because we need to change every host connected to the internet to be able to talk to each other after our change. This is why we still don't have IP multicast, we still don't have QoS, and why we are very slowly transitioning to IPv6 because this hourglass model just makes IP the narrow waist of the protocol stack. And basically that's all. The next lectures will be about just progressing into the more technical parts of the internet and trying to understand the high level and the large scale structure of the internet infrastructure.